We're going to continue on to, I'm going to go with 14. Looks like a good number up there. All right, so we're going to talk about chapter 14 here, which is acid and base equilibrium. Obviously not on the exam, which is on Tuesday, if I'm not mistaken. So this will be exam 2 material. And as I mentioned before, exam 2 material is usually the most difficult for students in this class. Again, it is like the hub of, you need to understand conceptually what's going on in these chapters here to make sure that you do the math correctly. So let us get into it. In the previous chapter, we talked about obviously just regular acid and bases and weak acids and weak bases. In this chapter, we're going to cover buffers. We're going to cover titrations, everything you did not want to know about titrations. And that will be it for this chapter. And we'll continue on in the next one. So let us talk about one important sort of aspect of really sort of buffers. And this is what is referred to as the common ion effect. And the common ion effect basically will shift the equilibrium basically away from obviously the common ion. And the presence typically of a common ion will suppress the ionization of a weak acid or a weak base. So what we're talking about here, let's take a look here. For example, if we had a weak acid like acetic acid, it would normally in solution, right, break apart into H plus and some acetate. Yeah. Now, since this is a weak acid, right, it's going to kind of mainly together, but still going to produce our H plus and our acetate on the right-hand side there of the equation. That's why it is still an acid. It's able to produce that H plus. Now, in a normal dissociation process here, we would have this weak acid basically dissociate into H pluses and acetate. We will still have the acetate. This guy here will set up basically an equilibrium in solution. So we'll have a little bit of everybody in the actual beaker or whatever you got going, wherever you put your acetic acid, I suppose. Now, what happens though, if we take something like acetic acid and we actually throw in maybe something else with it, like say sodium acetate. Sodium acetate, as we talked about the other day, that is a salt. Yes, so that is like a salt that's generated from the reaction of acetic acid and something like sodium hydroxide. When we have a salt that goes into solution that is an ionic compound, it will basically 100% break apart. It is basically a strong electrolyte. It will 100% break apart into ions. So what will happen is this guy will 100% here break apart into some sodium and some acetate. So again, if we sort of threw both of these things into the same beaker, we have a little situation that occurs here. We have our weak acid setting up our equilibrium here. And now we basically have just added 2 ions to the solution, right? We've added some sodium and we added some acetate into the solution. The common ion in this case is the acetate, right? So the common ion here is the acetate. Sodium is nowhere to be found in the top equation. So basically what we're doing in this particular case is adding more acetate, yeah, to this. And when we do that, our good friend Le Chatelier's principle says that the equilibrium is going to shift which way? It is going to go to the left towards the reactant side. So by having this extra acetate in there, it's going to cause the equilibrium basically to shift to the left. And when it does so, that means that we pretty much have just shifted this equilibrium towards the acetic acid side, where the acid basically is completely together. And that is what it means that it will suppress the dissociation of a weak acid by having this common ion in place It will cause the equilibrium to shift away from the common ion based on Le Chatelier's principle. That will essentially keep the acid together. So the double jeopardy question is, what happens to the pH and the H plus concentration in this case, as compared to just acetic acid by itself? We'll start with the H plus. Compared to acetic acid by itself, if you took acetic acid with sodium acetate in there, would we expect the H plus concentration to go up, to go down, to stay the same? We would expect it to go down in this case. Again, because of that shift to the left, that means less of the acetic acid is going to break apart into H plus. That means we would expect this to go down. That means in terms of the pH in comparison to acetic acid by itself and this common ion solution, we would expect the pH to go which direction? Yeah, it should go up, right? So as our H plus goes down, our pH goes up. Because as our H plus goes down, that means we actually have more OH minus, right? They go together. That will cause the pH to go up. Will it go up to basic? Probably not, but it will be a probably higher pH than what you would have if you just had acetic acid by itself. Any questions on that there? So the presence of a common ion, like it says here on this slide, will really cause a weak acid. And even the same situation will occur with a weak base as well. It will cause that Le Chatelier's principle shift to where either the weak acid or the weak base basically will stay together rather than dissociating or breaking apart into ions. Remember that really the pH is affected by the presence of free H plus or OH minus, right? So in the case of a weak base, it normally will produce H plus. Having our common ion keeps it together. We produce less H plus. We see the pH go up. A weak base, on the other hand, normally produces some free OH minus. So we got a weak base that would normally produce some OH minus. Having a common ion would keep the weak base together. That means that my OH minus concentration would go down. My pH would go, well, my pH would go down. Yeah, because OH minus goes down, H plus goes up, pH goes down, right? So it would become a little bit more acidic, if you will, not really necessarily acidic, but more acidic than the weak base by itself. The pH would be heading downward because, again, less OH minus would be in that solution because of the common ion. Any questions on that there? So common ion problems, as we will see in just a bit here, are really what we refer to as buffer problems. But any presence of that common ion definitely keeps everybody sort of together. The effect, obviously, on the pH here is what we've been talking about. So why don't we take a look at a couple of these problems here, our problem involving common ion. But why don't we start first as a nice review for Tuesday? Let's just start with A first here. Calculate the pH of a 0.2 molar acetic acid solution, the Ka value 1.8 times 10 to the minus 5. So for now, just do part A and see what you come up with. Okay, let's take a look and see how you're doing. So we're just going to start with the part A here, which is what is the pH of a 0.2 molar acetic acid solution. I have a Ka value for acetic acid. This is really just a weak acid problem like we did in the previous chapter. So that's where we should start here. So part A, action there. We're just going to do our dissociation equation here for acetic acid. I'll do this way, I guess. Ka value 1.8 times 10 to the minus 5, I believe. That means we do need to do a ice table here. The initial concentration was 0.2, correct? So that is 0.2. We'll have 0 and 0. Change would be minus x, plus x, and plus x. That means at equilibrium here, we get a 0.2 minus x, x, and x. Any question about the ice table there? All right, at this point, this will go into our Ka expression, which again should be our products divided by our reactants here. So putting in our numbers gives us an x squared 0.2 minus x equals 1.8 times 10 to the minus 5. Might as well take an assumption here. We're going to assume that x is equal to 0. In this case, it would just be obviously the 0 at the x on the bottom there. That gets us x squared 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply the 0.2 to the other side, and I'm going to also take the square root in the same move. So we're going to take 1.8 times 10 to the minus 5 times 0.2. I then need to do a little square root action on it. That's a lot of buttons. So let's see what I got there. That is an x is equal to, yeah, we'll call it 1.9 times 10 to the minus 3. We do want to check it. So to check it, remember, we're just going to divide it by what we were going to subtract it from and times it by 100. And I believe we should be good here, I think. It's like a 0.9%, so the check is good. Yeah. That means much like what we've done before, we are really interested here in the H plus concentration, which we can see from our ice table is equal to X. That means that really this guy down here, put a little molarity on it there, will equal our H plus concentration. That gives us a pH of minus the log 1.9 times 10 to the minus 3. If I could grab that calculator. Minus the log 1.9 exponent minus 3 there. Going to give us an opening pH here of 2.72. Any questions on any of those steps there? So this is, really just a straight weak acid type problem like we did in the previous chapter. It does make sense. We got an acidic pH here, and it's a weak acid, so that's good. Again, if you got a very high pH here, something went wrong with your calculation. All right, so this is our acetic acid by itself. What we're going to do now in part B is basically take the acetic acid and dump some sodium acetate in it. And in this part B, we're going to take a solution that has acetic acid and sodium acetate together. And in this case, between acetic acid and sodium acetate, the only one that's going to set up the equilibrium in solution is which one? It is the acetic acid. Again, as we talked about earlier, this is really a strong electrolyte, which means once it goes for a swim, it is not going to stay together. You're going to produce some sodium ions. You're also going to produce some acetate ions in this case, right? Obviously, much like the previous example, it is going to be the acetate here that is a common ion that's important. So let's see how this kind of affects the calculation. So we could approach this the same way because in part B, it is the acetic acid that's going to set up the equilibrium. That is where we could start again with our acetic acid, breaking apart into H plus and our acetate. By the way, since it really is the acetic acid setting up the equilibrium, the Ka value we would use is the exact same one, right? It is basically the same guy. As we just talked about, in addition here, we do have our sodium acetate happening, which I'll just write it above, sodium acetate, again, as I wrote on the previous page, sodium ion and our acetate, which obviously is our common ion we are talking about here in this equilibrium. So initially here, we would approach our ice table kind of the same way. Initially, we had still 0.2 of this guy. We have 0 of this guy. Do we have any of the acetate initially? We actually do, and this is why. So they were both kind of dumped in there together into the solution. We're going to get the acetic acid that's going to set up the equilibrium, but we do have that additional acetate that's floating around from the sodium acetate. It was 0.3, I believe, right? So that means that the concentration of the acetate, because it's a one-to-one relationship between sodium acetate and acetate, would also be 0.3 molar, right? So with the sodium, but we're not interested in that. So this right here, when people do an ice table for common ion problems, is a problem for most people. Most people are so used to, at this point, zeroing out that side that they just automatically zero it out. If I zeroed out that, what type of problem did I just do again? The one on the previous page, basically, right? It's just a weak acid problem. So in a common ion problem, you got to have an initial ion on the right-hand side that has a concentration. Otherwise, it's not a common ion problem. So that's a very, very common, huge mistake that people make, is they like zero out both sides of that thing. The rest of the ice table pretty much going to be the exact same deal. So we're going to have our minus X, our plus X, and our plus X. That means that when we get to equilibrium, 0.2 minus X, X, and also important here is 0.3 plus X on that side. Just like before, the equilibrium is the acetic acid, which means, again, we're going to be using the same Ka expression. So put in our numbers now, we have X times 0.3 plus X up on top, divided by 0.2 minus X on the bottom, equaling our 1.8 times 10 to the minus 5. Had good luck so far today, so why not continue? We're going to do the assuming X is equal to 0. In this case, we can eliminate the plus X, right, and the minus X. We got to keep the X by itself. Again, the reason for that is we're assuming the change is not going to be that much, but the X by itself started at 0, so whatever it gets is a lot, right? So we can't obviously get rid of it. That's going to reduce us down to X times 0.3 divided by, I'm going to try to write here, 0.2 equals 1.8 times 10 to the minus 5. So here again, we're going to multiply the 0.2 to the other side, maybe 0.2, there we go, times 1.8 to the minus 5. We're then going to come back and divide by the 0.3. So we're going to bring the 0.3 to the other side and divide. That is going to give us, that's a lot of zeros, an X value of, looks like 1.2 times 10 to the minus 5 in this case. Just like before, probably should check it. I think we'll be okay, but we'll do it. We'll divide it by 0.3. We'll times it by 100%. 0.3 times 100. That's 10. It's like 100. I'll try that again. Times 100. There we go. It's like 0.004%. So I think we should be good on this check as well. That again, in terms of the pH, that's important, is going to be our H plus concentration. So just like before, that should be our H plus concentration. And that means that we should be pretty much good to go in terms of going into our pH. So our pH would be minus the log 1.2 times 10 to the minus 5. And we open up here with a 4.92 pH. Any questions on any of those steps? So kind of like a traditional ice table here, the key is you got to have that initial concentration of that ion. Otherwise, you're really just doing a weak acid problem again. Any questions? Yeah. It really doesn't. I just took the larger one and it worked. If it works for one, it probably should work for both. If you want, you could check them both. But usually, you know, you should be good if one works for sure. Yeah. The 0.3. Yeah, it was part B of the original question. It was we basically took 0.2 molar acetic acid and mixed in some 0.3 molar sodium acetate. So it came from the original question. Yeah. Yeah. There is no, so we didn't have to do a square root if that's what you're asking. So in this case, we didn't do a square root because there was no x squared. So basically when we did this part here, we multiplied that to this side, right? And then we took this and divided. What that left was just x. So that directly left x, whatever we ended up with at that point. Yeah. We didn't have any x squares because we basically assumed that the top x, the other top x was 0, basically. Yeah. Other questions on that? Yeah.
Why? I don't understand why we say that's a process. Wouldn't it be going the other way?
Why? Say again?
Because of Molar's principle.
Yeah. Yeah, so I think what I'm going to say right now will answer that question for you. So let's compare really what we see in both of these cases, right? So the pH of acetic acid by itself, right, was 2.72, right? With really an H plus concentration of 1.9 times 10 to the minus 3, right? When we tossed in the common ion, the sodium acetate, as you correctly just said, it should cause this equilibrium to shift this way, right? And let's see if that happened. What that would mean is we should have more or less H plus at this point. We should have less. And that's what we see here, right? We ended up in this case with 1.2 times 10 to the minus 5 versus 1.9 times 10 to the minus 3. So your question is, it actually did shift it to the left. The end result of adding it, once it reached equilibrium, was that it actually did shift to the left at the end of it. You know what I'm saying? Yeah. So I know your question is, shouldn't we do the change like minus is on the right and plus is on the left? And the reason we don't do that is the overall sort of effect of adding it together with it is it causes it really to go to the left. And the result of that is we will get less overall H plus coming off of that acid than we would see if it wasn't there at the beginning. Right. So this is like the map behind like it shifts to the left, basically. You know, when we add it and stuff like that. Because remember, when we do add something like that, it kind of screws up the initial acetic acid equilibrium, right? So then it readjusts, and by the time it readjusts to the left, the end result is, as we see here, we ended up with actually less H plus than we had in just the acetic acid by itself. And the result of that is we had less H plus come off, which means the H plus concentration went down, pH went up, right? And again, here it did go up to basic, but it started at 2.72, but with the addition of that common ion, we did see the pH start to rise because of the less amount of H plus that came off. Other questions on that? Yeah. No, so it would be basically like what we talked about with Q that time, you know, like we had a problem like that, right? Where, you know, you're really given the starting amounts of everybody. So you could calculate Q and decide which way it would shift. In this particular case, you really couldn't kind of calculate Q in a sense, right? Because you don't really know what the H plus concentration is, right, initially. So you can't really do that. So it would only be a situation like, you know, I think we did an example where we had starting amounts of everybody. You're not sure you're at equilibrium or something like that. That would be a question like that. Yeah. You probably won't run into too much of that. And like pretty much in all of these problems, it's probably pretty safe to assume in terms of just specifically the minuses and the pluses that it's heading towards the product side in this case. Because really, when you think about a weak acid or a weak base, right, or an acid or a base in general, their purpose is to give away the H plus or the OH minus, right? Is to basically break apart, dissociate. So that's why it was safe to assume in these problems that it is heading from kind of left to right reactants to products, and minuses on their normal reactant side and pluses on the product side. Yeah. Other questions? Okay, so what we see here is a couple of things like we would expect. We did see the overall effect of having that common ion basically had the equilibrium shift to the left, kept this guy together more, had less of this H plus that was actually there at equilibrium. And that's really when we do calculate technically the pH is the H plus concentration at equilibrium. When everything sort of settles down, you know, and it gets to that equilibrium stage is essentially when we calculate it. So in problems that do involve these common ion effect, you know, we usually get starting concentrations of the weak acid and salts, And as long as they are relatively large values, we can actually assume that our initial concentrations are the equilibrium concentrations. So what that means, if we go back and kind of look at the example that we did, and we actually went back and plugged into here the X values, right? So if I took 0.2 minus 1.2 times 10 to the minus 5, what will I end up with? I will actually still end up with about 0.2, yeah? And same thing, I take my 0.3 plus the 1.2 times 10 to the minus 5, I will still end up with about 0.3. So because of that common ion is keeping that acid together, we're not getting a heck of a lot coming off, which is why our assumption kind of worked as well. We didn't have to worry too much about it. So in these situations, there's actually a way you could calculate the pH without necessarily having to do a nice table. And that is with our good friend, the Henderson-Hasselbalch equation. So if we do some substituting here, we get the Henderson-Hasselbalch equation. And this is an equation that we could use really in a common ion effect type problem. And really, as we'll talk about in just a second, a buffer is pretty much, this is your go-to equation right here. The pH is equal to the pKa plus the log of the conjugate base over the acid. The pKa value is calculated by taking minus the log of the Ka value. So this is the one that you could use to actually calculate the pH of a solution when you have a common ion, which is essentially buffers problems. There is a couple of other similar equations. There is one that does POH, which is the pKb value plus the log of the acid over the base, where the pKb is equal to minus the log of the Kb value. Sometimes people will use that one for basic type things, right? OH, right? So sometimes people will use it for basic buffers and common ion type situation. There's also a nice relationship that if you take the pKa plus the pKb, it equals 14, kind of like the pH scale. So that's sometimes useful. Maybe you got a pKb value, you want a pKa, you know, you could kind of convert it. I personally think this is your go-to, yes, in all situations, that the pH is equal to the pKa plus the log of the base over the acid. Why do I think that? Well, you could use it for acidic conditions, neutral conditions, basic conditions. You can use it for any conditions you want. And probably 9 times out of 10 in these type of problems, which eventually will be really buffer problems here, 9 times out of 10, you're asked to calculate the pH, right? Very rarely are you like, what is the pOH of the solution? So if you happen to use the top one, which is perfectly fine, you still then at the end got to take the 14 minus it probably to get to the pH. You might as well just go into the Henderson-Hasselbalch equation and get the pH is what you're looking for anyway. So I would go for that. Just for a side note, if you do use this or see this used, it is a couple of different things. Again, it's the pKb, and it is acid over base versus base over acid, yeah? So again, personally, I would go with this one, which is the one that's in the box, and just go with that one for basic conditions, acidic conditions, and you should be in good shape. Again, if you want to use the other one, sometimes you'll see people use the other one. But again, in a lot of cases, you'll have to subtract the 14 anyway. So might as well just directly calculate the pH rather than having to subtract the 14. Any questions on that? So let's talk about then how to use this maybe here. So if we look at the problem we just did, we had basically acetic acid that was 0.2 molar. We had sodium acetate, which was 0.3 molar. And we had the Ka value, which was 1.8 times 10 to the minus 5. So as soon as you see like, hey, I got both of these together, you should recognize that they are related to each other, right? Acetic acid and acetate, like acid conjugate base kind of deal. Yeah, they are related to each other. The sodium is there just to balance out the charge. Yeah, spectator ion, it's part of the salt, not really doing much in the situation. And we know it's not doing much in the situation because it's sodium, which means it's neutral salt. So not really doing much in the pH. As soon as you see that and recognize that they are related to each other, you got some good concentrations there, you could roll right into calculating the pKa value, which would be minus the log of the Ka, gets you a minus the log of 1.8 times 10 to the minus 5, gets you a 4.74, I believe. I'm like a memory loss right now. Let's try that. Make sure I did that right there. There we go. Now we could go into the Henderson-Hasselbalch, which is the pH is equal to the pKa plus the log of the base over the acid. That is 4.74, which is our pKa value, plus the log. Which one is the base here? Yeah, it is the sodium acetate. The other one is acetic acid, which is a big hint. But, you know, the base most likely will have perhaps one less H plus, right, than the acid. So it is going to be 0.3 divided by 0.2, and that should get us, it was 4.92, I think, right, is what we end up with there. So we could have done the previous problem without doing an ice table. You could have used the Henderson-Hasselbalch equation like we just did here, and you can see you will get exactly the same answer without the need for an ice table. So in these common ion situations, you could use the Henderson-Hasselbalch to calculate the pH, which are, again, really buffer problems as well. Any questions on that there? Side note is this equation here should only, write that big, only be used in buffer situations, which are basically common ion. And I say that because people learn this formula and decide every calculation, I got two numbers, why not? Let's just throw it in and hope for the best. And it's probably not going to work out well for you at that point. So don't go crazy with this. Again, this is specifically in the common ion buffer situation, which is, again, as we've been talking about, that conceptual understanding of when you see a problem, you know, is it okay to use this or is it not okay to use it? You will definitely come across several problems where it is super tempting, especially as we get into titrations, like I got two numbers, I got this equation, you know, I want to use it. So don't use it in every situation. It needs to be used in the correct situation. Any questions? All right, so let's try one here. What is the pH of a solution that contains 0.3 molar? I can go with formic acid on that. And a little potassium formate. Could be right, could be wrong. It's a 50-50 chance. This could be right. Ka value for formic acid, 1.7 times 10 to the minus 4. All right, so let's take a look. So as mentioned before, this is formic acid. This is potassium formate. They are related to each other. We do see a Ka value, which is related obviously to the acid. We know that this guy really is a weak acid, which means, you know, technically speaking, it is going to break apart like so. This guy here is actually a salt, right? And it's going to 100% dissociate in solution, and it would break apart into K plus and obviously some formate action here, with obviously the formate being our common ion here. So we should be able to see that these two are related to each other. We know that that guy is the acid, and that means the potassium formate would be sort of like the conjugate base. You have two options at this point. You could ice table, and it's perfectly fine if you want to ice table like we kind of did on the other one. If you did, it would look something like this. This would be 0.3, this would be 0. And again, the main important part here would be this would be 0.52 needs to be there. The change would be minus X plus X or plus X, since this is a common ion. That's why you need it. 0.3 minus X, X, and 0.52 plus X. So obviously it goes into our Ka, solve for X, and get the H plus concentration to our pH. So that is one approach, perfectly legit. If you're comfortable doing it, you like ice tables, you absolutely could do it that way. The other way is you could recognize that they are related to each other. We basically got a weak acid and its conjugate base sort of happening here. Those are all the makings, as we'll talk about in a second here, of a buffer and the makings of our Henderson-Hasselbalch equation. So you could go right into the Henderson-Hasselbalch equation without the ice table needed. You do want to probably calculate the pKa value, which would be minus the log of the Ka. That is minus the log of 1.7 to the minus 4. And looks like maybe a 3.77 as our pKa value. That means the pH would equal 3.77 plus the log. Obviously, the guy with like the spectator ion oftentimes is the base. Not always, but a lot of times. That's going to be 0.52 up on top. The acid is obviously the formic acid, which would be our 0.3 on the bottom. And that would get us some type of pH. Let's see here. Plus 3.77. Looks like a 4.01 in this case in terms of our pH. Again, if you took the ice table approach, you should end up with the same. So you really do have options, not one right way or wrong way. It's just really your personal preference as to how to do it. Any questions on sort of common ion problems here? Okay, so the common ion problem, as I've been alluding to, really is a specific problem that we come across a lot in chemistry, and it is basically what a buffer is. So a buffer is really sort of common ion situation occurring. So let's talk about really a buffer and what a buffer is. A buffer is a solution that is made up really of a combination of one of two combinations. It is either the weak acid and the salt of its conjugate base, or you could have a buffer that is a weak base and the salt of its conjugate acid. So what do we mean by salt? It has a spectator ion. Like the previous problem was potassium formate, right? So that is the salt of the conjugate base. The previous problem to that was sodium acetate. It has a sodium ion. That is the salt of its conjugate base. That's what the salt part means. It's got a spectator ion that's really not doing much in terms of the pH of the solution, but it's there really to balance out the charge. We also know that those two things should be related to each other by a difference of really, besides the spectator ion, just one H plus, right? Our basic Bronsted-Lowry definition of acid conjugate base pair should only be a difference of one H plus. The important part of a buffer solution is both of those are in the solution to begin with. So they both go in for a swim to begin with. The weak acid, for example, sets up the equilibrium. The weak base, if you have a weak base one, sets up the equilibrium, but the common ion is going to be supplied by the conjugate base or the conjugate acid or the salt of those guys. A very wrong idea of what a buffer is this definition. A buffer is a neutral solution, and that's what a lot of people call a buffer. And that is not really correct. A buffer could be a neutral solution. A buffer could be an acidic solution. A buffer could be a basic solution. You can make a buffer at any pH you like along the pH scale. What a buffer is a solution that will actually resist changes in the pH, even when you add more acid or base to it. So when you add more acid or base to a buffer, if it's made properly, will resist big jumps in pH. What that means is if you had a buffer that started at a pH of 5 and you added some acid to it, after you're done adding your acid and everything was made correctly, the pH of that solution should still be around 5. Will it go down a little? It will. It will go down a little. Maybe it drops to 4.9 or something like that. But you will not see the pH go from like 5 all the way down to like 1 when you add the acid. Same thing if you started with that buffer at a pH of 5 and you add some base to it, it will keep the pH around a pH of 5. Maybe again, it goes up a little bit. Maybe it goes to 5.5, 5.2, something like that. But it will not go from like a pH of 5 all the way to like a pH of 10 or 12 or anything like that. So that is really what a buffer is. It's a solution that is able to resist really big changes in pH upon addition of additional acid or base to that solution. Any questions on that thing? So how is it able to really do that? So let's take a look and see if we can figure out how it's able to really do that. All right, let's just start with a non-buffer solution. That's our good friend H2O there. So if I take some hydrochloric acid, seems like a nice strong acid, and I add it to water, what's going to happen to the hydrochloric acid? Will it stay together? Will it break apart? It's going to 100% break apart into H plus and Cl minus, right? So what we just did there when we added some water to acid, or acid to water, whichever way you do it safely, what we just did is generate a lot of free H pluses. What would I expect happen to the pH of water when I do that? Will it go up? Will it go down? Will it stay the same? It should see a pretty big drop, right? We should see a pretty big drop in the pH of water. Maybe it starts at a pH of 7 if you had real neutral water, and then maybe it drops to a pH of 2 or something like that, right? Depending on how much you added. Again, the presence of that H plus increasing very quickly, making the pH start to drop a lot, and we see a pretty big jump in the pH, hence why water is not a buffer. If we take some sodium hydroxide, which is a strong base, and put it in water, because sodium hydroxide is a strong base, it also is going to 100% break apart into sodium ions and hydroxide ions here, right? Now, in this case, we didn't produce a lot of H plus, right? But we did produce a lot of OH minus, right? Really quickly. And because H plus and OH minus are tied to each other, what I would expect to happen is my OH minus went up. That means my H plus should go down. And we just made a lot of OH minus, which probably dropped my H plus concentration a lot. That means my pH should then go, yeah, the pH in this case would then go up. So if we took our water, just say it was a pH of 7, by the way, water normally is like a pH of 5-ish range, but water, we'll just say we boiled it and got it to a pH of 7. When we add that base to it, and maybe it goes from 7 all the way up to 11, 12, something like that, a really big jump in pH. So in a non-buffer situation, if you take an acid or base and add it to a non-buffer, when you add the acid, you create a lot of free H plus really quickly, causing the pH really to change a lot because the concentration of H plus goes up a lot. When you add a base to a non-buffer solution, you create a lot of OH minus really quickly. The result of that is OH minus goes up a lot, H plus drops a lot, pH goes up a lot. You see these really kind of big swings in pH when you have a non-buffer situation. Any question on a non-buffer situation? So let's see what happens if we take both of these guys and add it to a buffer. So let's just do everybody's favorite buffers when they talk about buffers, which is our acetic acid and our sodium acetate. So again, this is a buffer because this is a weak acid and this is the conjugate base or the salt of the conjugate base. Again, in the buffer beaker, they are both in there. So we got some acetate floating around, we got the acetic acid floating around. So when you think about a buffer, it kind of has like an acid component and a base component in it together to begin with. So when we now take our hydrochloric acid and decide to dump it into our buffer, which over here has some acetic acid floating around, has some acetate floating around, got some H plus really floating around, and some sodium floating around as well. So when I take my HCl into here, it will react with what thing? Will it react with the acetic acid? Will it react with the acetate? So when we have acid reactions and base reactions, right? They're called acid-base neutralization reactions, acid-base reactions. We haven't really talked about an acid-acid reaction, right? Or a base-base reaction. Sounds funny, right? That's why they're not called those things. So when we add an acid, we would expect it to react with a base. And the base part of the buffer in this case would be the acetate. So when we dump the HCl in here, we're actually going to get a reaction between the HCl and the sodium acetate, or really just the acetate part is really the thing happening here. In case you're not sure, this is like a double displacement situation. Yes, positive, negative, positive, negative. The H and the acetate come together to make acetic acid. And then we make our good friend sodium chloride, right? So when we add the acid to our buffer, we actually get a reaction that occurs. We produce acetic acid and we make some sodium chloride. So let's analyze the two things we just made in this reaction. First off, we made some acetic acid, which was part of the buffer to begin with, right? So clearly it was part of the buffer to begin with, probably not going to screw up the pH all that much, right? We made sodium chloride, which is a salt. What type of salt is our sodium chloride? It is a neutral salt, which clearly is not going to screw up the pH. But really the main reason why we don't see a really big jump in pH is actually for something we do not see here. So what do we not see on the bottom that we do see over here when we put it in water on the product side that would affect pH? It's a letter in the alphabet. H plus, yes. So when we put the HCl in water, we produce a lot of H plus really quickly. And it's really the free H plus, right, that affects the pH, hence the pH equation, which is minus the log of the H plus concentration, right? So when we put it in water, it made a ton of H plus all over the place, causing the pH to change a lot. Here, we did not produce any free H plus, which means if we didn't produce any more free H plus, that means that the concentration of H plus remains relatively constant, right? And if the concentration of H plus stays relatively constant to where it started from, that means my pH will also remain relatively constant because we didn't produce more H plus, right? So the way a buffer is able to prevent really big changes in pH when you add an acid to it is because it has the base part, it's able to react with the acid that's being added. It prevents the formation of a lot of free H plus really quickly. And that keeps the H plus concentration relatively constant and the pH stays relatively constant. I say relatively constant because if you put a pH meter in it and you checked it, the pH would drop. And it would drop because technically you created a little bit more of the acetic acid, which by definition will let a little bit of H plus out, right? So what we end up seeing here is maybe the pH starts at 4.74 Maybe it drops to like 4.6 or something like that. Not a giant jump in pH. It doesn't drop from like 4.7 all the way down to 1 or anything like that. But it does go down in the correct orientation, which in this case is down because we're adding acid. But you won't see a tremendously big jump in pH. Any questions on that there? So let's take a look then at what happens with when we add sodium hydroxide to the same buffer. Let's just erase these guys here. Get rid of that. There we go. That's over right here. So let's say we took our sodium hydroxide and we added it to our same buffer, which was our acetic acid sodium acetate buffer. Again, in the buffer, because the acetic acid sets up the equilibrium, we got really the acetic acid in there, got a little bit of H+, and we got some acetate floating around. Again, we got the acid part and the base part in the buffer to begin with. Now, when I add my sodium hydroxide to my buffer, it is going to react with which part of the buffer in this case? It's going to react with the acetic acid, right? The acid part of the buffer. So again, this is your acid part. That's your base part of the buffer. So when you add a base to it, it should react with the acid. And we get a normal kind of acetic acid sodium hydroxide reaction that's going to occur, also like a double displacement deal. We are going to make a little bit of water and we will make some sodium acetate. Again, when we look at how this reacts with the buffer and we see what we produced over here, we clearly produce water, which shouldn't screw up the pH. Just like in the other case, in this case, we actually produce some sodium acetate, which is part of the buffer to begin with. So it shouldn't mess up the pH all that much. But again, it is what we actually do not see on this side that we did see on the previous page when we added the sodium hydroxide to water. When we added sodium hydroxide to water, what did we see get produced? Yeah, we saw hydroxide get produced. When we add that same sodium hydroxide to our buffer, we do not see any free OH minus being produced. And the same logic applies because, again, H plus and OH minus are related to each other, right? One goes up, one goes down. If we're able to keep the OH minus relatively constant, that means that our H plus concentration should also remain relatively constant. And by default, that means that our pH here should also remain relatively constant as well. So in the case of adding a base to a buffer, it basically will react with the acid part of the buffer. It will prevent the formation of free OH minus. And by keeping that free OH minus from being formed, it by default keeps the H plus concentration relatively constant, and thus the pH also relatively constant. Again, I say relatively constant because if you stuck the pH meter in there, you would see the pH go up a little bit. So in this case, you know, maybe we start at 4.74, maybe it goes up to 4.95, something like that, but it will not go up to it won't go from 4.74 all the way up to like a pH of 12 when you add the base to it. So this is really how a buffer functions. It prevents really those two things from being formed, which is the two things that can really screw up the pH. It prevents the formation of free H plus when you add an acid. It prevents the formation of free OH minus when you add a base. Both of those things basically allow the H plus concentration to remain as relatively constant as to where it started from, and your pH stays the same, relatively constant from where it started from. Any questions on any part of that? Another really important thing that we see here is, let's steal this page too. Let's do this. No, that's what you're reading for. All right, let's go with that. So what we really see is, if you think about a buffer, is, you could kind of think about a buffer. A lot of times when you make one, you actually want, so there's like the acid part and the base part of your buffer. A lot of times you want to keep the acid part and the base part relatively close to each other, have a pretty good concentration of both of those things, because those are really the part that's going to react when you add acid. So when we add acid to this buffer, what we see is the acid will react with the base part of the buffer, but we also see that it actually will make, over exaggerated here, but will make some of the acid part. It will use up some of the base part, but it will make some of the acid part. In a sense, it's sort of self-regenerating as you're doing the buffer here. So at least part of it gets regenerated. When you add base to a buffer, it will react with the acid part and make some more of the base part of the buffer. Always happens that way. Again, over exaggerated drawing here. We make some of the base part of the buffer. We use up some of the acid part. So there is a limit to how effective a buffer can be. It's sometimes called buffer capacity. What would happen if I did not read the instructions? Never happens. I grab the bottle of acid. I'm supposed to be adding like 0.1 molar, but I grab like the 18 molar. It seems like it's going to be the same thing. And I dump a bunch of 18 molar acid into my buffer. Or I just keep dumping acid into my buffer. What would eventually happen if I just keep dumping acid into my buffer? Well, if I keep dumping acid into my buffer, I'm going to continuously use up my base part, right? I'm going to keep using up my base part. I'm going to keep using up my base part till at some point there is no more base part, right? To react with the acid I'm adding. And if I keep adding acid, now what am I doing? I'm just dumping in a lot of H plus at that point, right? So at the point where you blow through your buffer and you keep adding acid because you didn't follow instructions, you're going to blow through the buffer, and at some point you will start adding H plus, and it's at that point you will start to see the pH start to jump a lot, right? It will start to go down a lot. Same thing would happen if you just randomly or decided I just want to keep adding my base. You will eventually kind of use up all the acid. You'll still be making this guy, but at some point you'll just be dumping in a bunch of OH minus, and at that point where you kind of blow through your buffer, you actually will again see a big jump in the pH. So there is a limit to how effective a buffer can be, and it has to do with how much you add and the actual concentration as well. So like I said earlier, if you made a buffer that had a concentration of 0.1 molar, for example, your actual buffer was 0.1 molar. When you go grab off the shelf the 18 molar hydrochloric acid and you dump a bunch in, there's just not enough base in that buffer to handle what you're putting in there. It's going to basically chew right through it, and you will see a pretty big jump. How do I choose what to make my buffer from? That is where our Henderson-Hasselbalch equation can be very helpful. So as I mentioned before, a lot of times you kind of want almost equal amounts, not in all situations, but that's a good starting point, which means technically if I had equal amounts of the base part of the buffer and the acid part of the buffer, my Henderson-Hasselbalch equation would be the pKa plus the log of 1, yes? This guy would be the same. Log of 1 is equal to 0, which means if you ever want to choose what you should make your buffer out of, you typically want to choose an acid or a base that has a pKa value of plus or minus 1 of your desired pH. So for example, if you wanted to make a buffer at a pH of like 4.6, acetic acid is a great one for that. As we saw earlier, 4.74 is the pKa value for acetic acid. That's pretty close to your desired pH. You wanted to make a buffer of like a pH of 9.25, would acetic acid still be a good choice? It would be probably a pretty crappy choice. Yes, in order to do it, you got to put a ton of stuff together to get it there. Something like ammonia and ammonium and ammonium and ammonia would be a good choice. pKa value for this guy is actually 9.25. So you would want to make your buffer out of ammonia, which is a weak base, so you could do it, and ammonium, which is this conjugate acid, so you could actually make a buffer of that. So sometimes you're asked to choose what you should make your buffer out of. You would want to go to like a Ka table, Kb table, figure out the pKa values of all your choices, and you would want to choose one that's really the closest to your desired pH, because again, you can make a buffer at any pH that you want, and that would be the best way to do that. Any questions on how buffers work? How to choose the right thing to make a buffer from? You need to know all this, yes. How to do something, sorry. Okay, let's see here. So this again is a little graph of a buffer solution versus water. And as you can see, water is definitely not a buffer. And we do see water starting out here at a pH, just adding a little bit of moles of HCl. We see a fairly big drop there in the pH really quickly, as opposed to here with our buffer, able to maintain a really constant sort of pH all the way across. All right. So which of the following would be good buffer systems? So take a minute or two and see what you come up with. So first off, you want to determine if it's a buffer or not. What we're looking for is either a combination of a weak acid and its conjugate base, or really a weak base and its conjugate acid. One thing you should know about these two things from our Bronsted-Lowry conversation is they should really only differ from each other by 1 H+. Again, they may be a salt, so they may have like a sodium, a potassium, something else in there. But the main two things, again, should only differ from each other. So when we look at KF and HF, first off, are they related to each other? The answer is yes, they are related to each other. That is hydrofluoric acid. And really the part that is related to each other is, this is really F-, right? It's the K+ there, not really doing much, just a spectator ion. Since HF is a weak acid and that is its conjugate base, would this be a buffer solution you can make? This would be, yeah. So this definitely would be a buffer solution. Any questions on that one there? KBr and HBr, are they related to each other? They are. Again, the K not really important here. This is Br-, and that is HBr. So those two are related to each other. HBr is what type of acid? It is a strong acid. Yeah. So can this be a buffer? It cannot be a buffer because it is a strong acid. So let's just take a moment and think about that. Why can I not have a buffer that is a strong acid or a strong base, by the way? Why can you not actually have a buffer that is strictly a strong acid or strong base? They will not set up equilibrium, I think is what he said. Yeah. So, yeah. So if you have something like a strong acid like this, right? It is going to 100% break apart into H+ and Br-, right? And as we just talked about, the way a buffer works is it has in solution an acid part and a base part, right? Which means in this case, you only have really the conjugate base part. You don't have the acid part anymore. So anything that is a strong acid or a strong base, because it 100% breaks apart, it can't set up that equilibrium that's needed basically to keep the acid part and the base part in solution. And that's why buffers are made up of weak acids and weak bases, because they set up that equilibrium. It provides a good way to keep both of those things in solution at the same time and relatively good concentrations. And that's why it's able to function the way we just talked about it. When you have a strong acid or a strong base, you only get one part of it, which means essentially if you add some acid to this, you're just going to keep dumping in some more H+. You're going to see a pretty big jump. It will not be able to function as a buffer because it really only has the base part here. So that is why you cannot have a buffer that is a strong acid or strong base, not to be confused with something you may read or may talk about, which is you can actually make a buffer from a strong acid or strong base. But by the time the buffer is made, the strong acid and strong base are long gone. So you can actually produce a buffer by reaction of those things. But the buffer itself can never be a strong acid or strong base. That leaves us part C here. That is really hydrogen carbonate and carbonate. Yes. Again, the sodium there is just a spectator ion in both cases. This actually comes from carbonic acid, which is a weak acid, which means will this be a buffer? Yes. Kind of use that in our body a little bit, right? Carbonated buffers. So that would be a buffer as well. Any questions on that? Yeah. Is not. So the question here is if you put both of those things in the solution together. So if you piled in HBr and KBr into solution, basically what you would have floating around at that point is H+, K+, and Br-, right? So basically the only thing you got in that solution is the base part. You have no acid part. When we did with the HCl and the acetic acid and sodium acetate buffer, what we had in solution was really the acetic acid, the acetate, and some sodium. And this guy is going to set up an equilibrium with this guy and this guy in solution. That keeps the acid part in the solution. That keeps the base part in the solution. And that is actually the buffer. The HCl wasn't the buffer. The HCl was being added to the buffer in the previous example. Yeah. Other question? All right, we will stop there today.